what thermodynamic processes make the most sense as reversible processes? This is a strangely worded question because it just says make the most sense, because it turns out all of them can be modeled theoretically as reversible processes. In other words, there's ways to imagine each of these processes so that they occur in a way that does not cause an irreversible change to the environment, and therefore satisfies the condition for being reversible. And another way of looking at that is there's ways to do it that, at least in principle, you could imagine taking a video, maybe including like infrared footage so that you can see all the thermal effects that are going on, in such a way that when you view the video in the forward direction of time and then view it in the reverse direction of time, you don't see any violation of laws of physics happening in either case. And what would be an example of like a violation of a law of physics, or maybe I shouldn't say law of physics, even just common sense, although oftentimes that does relate. Well, one example would be if you take two objects and one of them is cold, and by that I mean at a low temperature, and another one is hot, and that means at a higher temperature, and if you put them in contact with each other and heat flowed from the cold object to the hot object without any assistance from the environment, that doesn't really make sense, right? And it turns out we're going to be able to see later on that would entail a violation of the second law of thermodynamics. So that's why I hesitated for a second there, because I realized, well, we actually haven't discussed that law yet, but that's the way it's going to turn out. There would be a violation there, but it also violates common sense. Normally, if you take a cold object and put it in contact with a hot object, the cold object will warm up as the hot object, the higher temperature object, winds up transferring heat into the cooler object until at some point the temperatures are equal, and then that stops. And that represents an irreversible process. But we're being asked here about how these might make sense as reversible processes. Well, the only way for it to make sense is to maintain equilibrium conditions, in particular thermal equilibrium conditions, both throughout the system of gas that is undergoing this process and between the system and any interaction it might have with the environment. And like I said, all of them can theoretically be looked at as a way that is reversible, but the isochoric and the isobaric processes are a little more troublesome in that regard, in particular because they change temperature, yet they also exchange heat with their environment. And so that means that in order to maintain conditions that wouldn't look wrong when you view the video, right, wouldn't violate the idea of normally a hotter object warms up a cooler object, you'd have to continually change the temperature of the environment. And you can kind of see the clues here in the chart because there's delta T's in both of the expressions for the heat of the isochoric and isobaric processes. That tells you heat is happening, so it needs to be in contact with the environment. And the delta T tells you, well, the temperature is going to change, because the only one that doesn't have temperature change is isothermal. That one does have heat going on, but because it's isothermal, it's more easily imagined how this could happen in a way that if you took a video, you wouldn't say, okay, something is weird about that, because you just do it in contact with a constant temperature environment. And at least in principle, it doesn't seem to be a violation if heat can flow between the environment and the system, provided the two are at the same temperature. You look at that in either direction and you wouldn't say, okay, that's a clear violation of a law of physics. Now, it's really probably impossible to actually achieve that in reality, but at least it's not a clear violation. So we're kind of touching a certain edge of logic here, perhaps. But what I'm trying to argue is that isothermal is maybe unique in the sense that there is heat exchanged, but at a constant temperature, and that lends itself to an interpretation in terms of equilibrium conditions. Now, it says processes here, though, because we can include adiabatic as well, simply for the fact that its heat is zero, because it's adiabatic. And that means it doesn't even need to interact thermodynamically with an environment. It's still going to have exchange forces, you could say, do work, or possibly have work done to it, depending on the direction of the process, because of this formula right here, and this not being equal to zero. But that's okay because that's not going to create a violation of that simple rule that we said that a cold object should not warm up a hot object, which both defies common sense and defies the second law of thermodynamics, it turns out. So that means the answers are the isothermal and the adiabatic process. Both of those can be done maintaining equilibrium conditions that we can describe, we can imagine. With isochoric and isobaric, it's really hard to imagine because you'd have to continually adjust the environment in a way that would be probably difficult to film and very difficult to make, to run backwards and have people believe that that's really what's happening. So that's the argument I'm making. And like I said, because all of these theoretically make sense as reversible processes, this argument is not very strong. But what's cool about it is we're going to see later on that this is kind of the way that Sadi Carnot, who was the first person to really kind of develop some theory behind what is called today a heat engine. He was looking specifically at steam engines, and he was asking some questions about efficiency in steam engines, and he wound up deciding that the most efficient engine should be one that is based on reversible processes. And his argument was very elegant, and we're gonna look at it. And then later on, that physics was reviewed by a physicist named Rudolf Clausius, who wound up coming up with the law of entropy, which is another name for the second law of thermodynamics. And on the way, Sadi Carnot establishes an upper limit to how efficient any engine based on any kind of fuel that releases heat, in whether it's combustion. It turns out it can also be like nuclear fission releasing heat, so like a fuel rod in a nuclear reactor, for example, driving like a turbine maybe to create electricity, is going to be within the category of a heat engine as well. But this upper limit formula is actually based on the physics of the isothermal process and the adiabatic process, because they lend themselves the most to imagining how you could build a real engine entirely based on reversible processes.